Anthem humor, but there's a book we have in common. All right, I'm going to talk about parallelism in Clojure. Some of this has changed a bit since last week because Rich is always busy doing things. All my entire presentation is just going to be text like this, so you guys can just read along, maybe out loud, and I'll just advance page by page. But, so obviously, Clojure is excellent at concurrency. We have lots of concurrency primitives and constructs, and the goal, and Rich actually has some pretty ambitious goals in terms of parallelism, is to extend the constructs we have for doing parallel processing. And even more ambitiously, to see if we can do transparent parallelism, make that decision on the behalf of the processes, which is particularly ambitious. But so right now we have pmap, which I think most of you are familiar with. And there's the par branch, which many of you may have seen. I don't even remember when you first created that, and it's based on JSR 166 fork join by Doug Lee. And right now, it really consists of two public functions, pmap and pvreduce, which is for parallel vector map and parallel vector reduce. So really, it takes, the only arguments it takes are vectors at this point, but it takes advantage of the structure of persistent vectors in kind of interesting ways, which I'll go over. I do want to talk about, I want to start by talking about pmap, show how that works, just to kind of shed light on where it has strengths, where it has weaknesses, and if you understand kind of how it works, it's a little easier to understand. The first part of trying to do this work was looking at that code, Rich's code, which is very tight, and kind of unraveling and understanding what's going on and converting it to pictures, which is what pretty much how I like to think. I think Rich actually starts with pictures, puts it into code, and then I had to rewind and get pictures again to understand what was happening. So we'll start off, I'll go over pmap, its algorithm, some of its weaknesses. I've done some very minimal performance characteristics just to get a sense of how it compares to map. Show chunking, which is a way of improving its performance in certain circumstances. Then I'm going to talk about fork join in a at the most general level and show that algorithm. I'll quickly do an overview of persistent vector data structure, and you'll see there's a lot of similarities in that structure to the way fork join works. And then I'm going to go over FJV tree, which is the underlying function that's private right now, but I actually think it should be public. It stands for fork join vector tree, and it's what drives pvmap and pvreduce. It's private because it relies on using some private aspects of pv vector, and in order to make par work, we actually have to make those public. But I think that's actually a good trade-off, and I think if people see how they can do kind of general fork join processing in Clojure and understand the underlying data structures, I mean, there's a lot of possibly interesting things that people can be doing, and I want to encourage that. Then I'm just going to quickly show an example of creating a parallel version of a filter based on pvreduce. All right, so pmap, lazy meets parallel. So this, you're going to be seeing a lot of this particular slide. This just represents data that we'll be mapping or reducing over 4,096 individual points, which sort of hurts Keynote. But we're going to focus on a small subset of that to begin with. So pmap is lazy, or semi-lazy. And laziness and parallelism don't really go well together, kind of naturally, you would think. So it's semi-lazy. So it's looking at the number of processors that are available. In this case, I have just 2 processors, and it's going to add a couple more threads. So you'll end up with 4 threads. And it's going to create futures. It actually creates 4 futures in this case, which each run in kind of a cached thread pool. This is the thing that Rich has just changed. It made it so bindings pass down to these threads, which it didn't do before, making future much more powerful than it was before. But it's lazy, so it spins up these things, and then as they complete, so this first one's completed, no more threads will be spun up until it's been consumed. And once it's been consumed, a new future will be created. You can see now we've got 2 of them that are completed, but it won't spin up anymore. And then it just basically just walks through trying to stay ahead of the person, or the consumer of the data. Now, this can lead to a problem. If the consuming process is slower than the process that's actually producing this data, then these things are going to finish up, and no threads are going to be utilized. It's lazy, but you've lost parallelism completely. So now they've consumed the first item, and now you've got one feature going, and on and on and on. So instead of using your 4 processors, you're really just getting one at a time. And this is the weakness, or with laziness and parallel when they meet. So another area where pmap could possibly have issues is if the load is not even. So we've got a process, this orange process, which is still running. Everything else has been consumed, and we're just going to, the consumer is now pulling off from the front, but this guy is not done. And as we move forward, now all the features are complete. The processors, the 3 processors are idle, and we have to wait for that guy. Now he's complete. We can consume, and then wait, and wait. So this is one area where pmap is potentially a problem. Now, everything I've looked at, I haven't been able to simulate a situation that would really make this effective, but fork join has a way of dealing with this, which is called work stealing. All right, so I need to point to this thing. All right, so this chart represents, it's the difference in performance from map and pmap based on the function that you're passing. So I've basically got a test function that I can control the duration that it runs. So up there at the top, it's 0.0005 microseconds, or milliseconds. So it's a relatively quick process. And then we come down here where we've got processes that will go on for 4 milliseconds. The faster your process is, the difference in performance between pmap and map is large in favor of map, so we all know that. You don't use pmap when you have a fast process. It just isn't worthwhile. This is on the left side, this is actually in percentage. So the difference in map and pmap, now, again, this is just one example and on a 2-core machine, and I would do a lot more before I make this kind of global statement. But in this particular case, it's 1,220 times slower. But it's a very short running process. This side is actually in just raw milliseconds, and you can't even see the time difference in milliseconds there. So it's not really, in reality, it's not a huge hit. Percentage-wise, it's massive. But as it gets bigger, as the time it takes for your function to run gets longer, the difference becomes kind of indistinguishable. So right here, it doesn't really matter. Map, pmap, there's no real discernible difference. And then where processes get longer, then pmap really starts to take off. And we've got, and again, this is the worst case scenario. This is 2 cores, not even hyper-threading, and you've got, what, 20%, that's almost a 200% gain right there. So that's really effective. And it just depends on the characteristics of the functions that you're mapping over. So one way to try and make your functions take longer effectively is to do this chunking. So we're going to look at a bigger section, and we're going to partition our data. I mean, it's just partition 32 is going to create subchunks. And then the function that we'll pass to pmap will actually be a function that calls map on that chunk. And then just does what we've seen before, but on just bigger segments. And this actually improves performance. So this is chunk sizes. We've got 2 at the top and 128. The total vector for this data was 512 in length. And so chunks of size 2 were still slower. This is compared to standard map, slower than standard map, but not too bad. And as the chunks get bigger, it's the same kind of region. We got a region here where it's sort of indistinguishable, and as the chunks get up to 128, then we're actually getting an advantage. Now this is for a function. This is the function at the top of the last chart. It's the fastest function, which is the worst case scenario for pmap. And this is just a way of trying to improve the performance of pmap in those situations, chunk it up. So you can, so there we go. This is one way to deal with that. All right, so that's pmap. So fork join is work Doug Lee's done. It's a divide and conquer algorithm for doing processing in parallel. So the first thing, it uses this concept of a deck, and I want to just quickly go over that so that's kind of understood. A deck is a double-ended queue. Fork join kind of iteratively breaks its task into smaller pieces. So here it is breaking a first job into a smaller task, putting half of it on the deck, and then continuing to do that. So what happens here is that the largest task ends up in the back, and then a job is processed, things come off the front, but the stealing or taking occurs at the back. Because the biggest chunks are at the back, it makes the work stealing algorithm more efficient that way. And so that's just an example of kind of how decks work, because the next set will get more extensive. So here we go. We have our original data set. This indicates, this is the chunk of work it's doing. This is the current thread. We've got 4,096 values in it. The first thing it's going to do is split that in two and push half of it onto the deck. And then it's going to break the current task, again, in half. And it's going to continue to do that. Let me go back. It's going to continue to do that until it reaches below the sequential threshold we have there, which is 256 items. Once it reaches 256, it'll actually do its process. But in this case, it'll just keep breaking it down. This particular example, we're going to have 4 workers. This is just a single worker. And we've got a key down here. Obviously, this represents a queue. This is the queue. This is the current thread. So this is now work stealing. So this is the second worker is going to pull off the back of the deck, take that chunk of task, and go with it. And it's going to do the same thing. It's going to split in half, put half of it on its own deck. And then 2 more workers come in. So now we've got all 4 workers with equal-sized chunks of data that they're going to work on. And they will continue to split the jobs in half and then push half of it onto their decks, and so on. So now we're at the point where we've got 256 values. This is the sequential threshold for this particular example. And they can actually do the work that they were intended to do. This is in the vocabulary of fork join vector tree, this is going to be a leaf node function. So we'll be passing a function in that will operate when we reach our threshold. And so then work completes, and each worker starts popping off things from their deck and doing computing on it. And then once they have a couple completed tasks, they can actually call a second function, a combine function in terms of a fork join vector tree, or just join in the generic fork join sense. And once that's done, they pop, break, push, and so on. Now I'm going, so this is the basic scenario. Let me go back there. So this is actually, and here's another example of work stealing. So this orange worker is operating a little bit slower than the rest. Everyone else is much further along, and the blue worker has completed all of its tasks and doesn't have anything else to do. But it sees that there's that work that's not being on the back of the queue for orange, and it just takes it and starts processing it itself. And then orange completes its task and takes back a little bit some of that. So this is the work stealing. This is really a way to deal with load balancing. It's those uneven loads where pmap potentially it's going to get stalled on a slow process or an uneven workload distribution, and there's no way to kind of work around that. Fork join has a way. Again, I haven't been able to effectively simulate examples that show this advantage, although going into statistics for a second, the variance of the performance of fork join is much tighter than it is for pmap. So on and on and on until the task is completed, joining everything that's been completed. All right, so how does this actually operate in Clojure? Now this is going to be a quick summary of persistent vector, which is not necessarily something that lends itself to a quick summary. But persistent vector has a tail and it has a root. And the root is a node. A node is just this is a Java object in Clojure. Root is an object that can have 32 children nodes. Well, it's a node that can have 32 children nodes, and tail is effectively, it's just an array that can hold 32 object references. As you fill up your persistent vector, the object references go to the tail until the tail is full, and then they get pushed into the root node. And then that continues until all of the 32 children nodes of that node are filled. At which point, when you create some more, you actually take that root node, and you create a new node, and you make the root a child of that. And so now we have 2 nodes each that have 32 nodes within them, and that just keeps filling up. And you kind of just grow your data this way. So you end up with a tree structure. And this square representation of a tree structure is called a tree view, which is what you saw in the fork join example. And none of this really matters for this example, but just as an overview, we've got this index, which is telling us the index value of this particular point here. We've got the green box, which gives you basically which node within this box are we talking about. The red refers to which child here, or the blue does. And the red is which of these children. So we've got 32, 32, and 4. So that's just a detail that really doesn't matter. But it's just to give a little detail on parallel vector, which is our persistent vector. So the key to using, the key to fork join was actually a Rich's approach to parallelism enclosure is to have it work on Clojure's existing data structures. This is kind of a different approach than what other languages are using. They'll create parallel versions of vector, parallel versions of map, and other things. So that's what we're. All right. So fork join, PV map and PV reduce are based on fork join vector tree. And fork join vector tree takes the vector and it takes a combine function and a leaf function. So this is the current thread. Same exact thing we saw before, except this time instead of splitting it in 2, it's breaking it into 4. We have a branching factor of 32, just like that persistent vector you saw before. The top level nodes, there was only 4, which is what's going on here. So we break it into 4, then we break it into 32. So instead of continuing to break with a branching factor of 2, now we're at a branching factor of 32. We take the current thread, takes the 32 object references, pushes everything else into the deck, and then calls compute. For PV map, this is the combine or the leaf node function. It's basically, we're just mapping. It takes in the node, which is that object that's private, that we need to make public. Takes in the node, it runs a map, since it's actually, it turns it into a Java object array. Runs a map on it, and takes the output of that and creates a new node. So in the persistent vector, this was a node. It does its process, it applies the function to it, and creates a new node. Then PV reduce, the leaf node function for PV reduce, is actually, this is doing a reduce. It's doing it with a loop and a recur, and that's just because we're dealing with the Java array for efficiency purposes. But it's going to loop through, it's going to apply that function to the return value from the previous loop through, and take it, with the second argument being the next value. So the output of this is going to actually be the single value that results from this loop. It's not going to be another node. So here's, the work stealing is going on, other workers are coming online, they take, they push, they compute. and then they get to the very end, do their computation, and then they're going to do the joins. The join function for pvmap is going to take this collection. The result of pvmap is going to be a collection of nodes. And it's going to turn it into an array and then use that in this constructor to new node. And so what we end up with is a node with 32 children nodes. And for PV reduce, it's actually just going to do a straight reduce on that result. So the output, the collection that's being passed there is just a straight collection containing whatever the results were of each of the parallel reduces. Until that's done. So, and let's just look at the performance characteristics for a second. So just like pmap, the faster your function is, the less effective pvmap is compared to map. And right now it's actually, it's 80% slower, which is actually much better than what we had with pmap. Then we get in the middle area where it really doesn't matter which, and then we get to the long-running functions where pvmap beats map by quite a bit, which unfortunately is only 20%. So this is, with the example I used on 2 cores, pvmap doesn't perform quite as well as pmap, which I've got the comparison here. So this is this long red line. This is the performance difference between pmap and map. And it's terrible. I mean, 1,200 times worse. That is pmap. So in the worst case scenario, pvmap is much better than pmap. And it goes that way. We get to this in the middle area where it really doesn't make any difference. And then we get down here, and percentage-wise, it's hard to see how much the difference, because we have this number is screwing up the scale. It's so bad. So we look at the raw numbers, and you can see pmap is really around twice as, you've gained, it's twice as good as map is at this point. pvmap is only around 75% better than pmap. There's actually a lot of performance improvements that can occur in the current versions of pvmap, and Rich is pretty confident that we can make that 10 times as fast. If that's the case, pvmap would be all around better. It would perform much better in cases where pmap performs terribly, and potentially perform better even in cases where pmap performs really, really well. So this is the same thing for reduce. We've got it's about 50% worse than PV reduce is about 50% worse than standard reduce. And in the best case scenario where you're running on long running functions, it's about 25%. And if we can improve that performance, then we have a parallel version of reduce available, which provides a huge amount of flexibility. For instance, we can create a filter function, just an example of one thing you can do. So this is PV reduce just operating on a standard plus. So we're just going to sum these numbers up. Effectively, what PV reduce is doing is it's going to run a reduce plus on a bunch of the results of reduce plus on vectors that it's broken into pieces. The output of that is just going to be the reduce plus on the numbers. And it works without a hitch. PV filter, the function for doing a filter with a reduce is to take, the function is basically going to have a predicate associated with it, and if the predicate evaluates true, it's going to conj the current value onto the vector that's being constructed. So which means you need to start with a base case, an empty vector. And it's just going to continue building a bit larger vector with values that pass the predicate. So here's even, a filter that should be looking for even numbers. So we have, it's going to be a reduce, calling that kind of inner filter function on the results of calling reduce on filter with an empty paren, or empty vector. And then we get to this point where it's going to blow up, because filter can't evaluate if this is even. So if you want to use the parallel version of reduce, you actually need to modify your function to be associative. to be able to run in cases where, well, you need to create a function that's associative. So in this example, we're going to evaluate and say, look at the arguments that's being passed to this par filter function, and if it's a vector, then we're going to apply reduce conj on it. And otherwise, if it's an even value, so it's not a vector, something that we can evaluate as even, then we just do the standard thing we did before. And finally, and otherwise, if it's not a vector and it's not even, then just return the first argument. So this is just a way of doing filtering that won't blow up with a PV reduce. So you get that, turns into that, and then it'll actually realize that these things aren't numbers. It's not going to call even on, it's going to call a vector. It's going to realize it's a vector, and it's just going to concatenate those two things together. So that's kind of the general strategy for using PV reduce, is to take functions that would normally work, non-associative functions that could work fine in reduce, and make them associative in whatever way seems best. So the performance characteristics for p-filter, it's essentially the same as filter. It does poorly when you have a predicate that evaluates very quickly, and you might as well just use reduce. As the predicate gets more complicated, it becomes a lot, it doesn't really matter. And as the predicate becomes more involved, PV filter becomes a better choice. So that's the references. So this is, the goals are primarily to make parallelism work with Clojure's existing data structures. And the fork join framework, the approach it takes is it works in a much broader range of functions. So places where pmap would fail, it's a very good choice. All right, questions? And I apologize for losing my thread there.